Hello, my friend. Welcome. I thought we'd have a bit of tea today and talk about chemistry. I brought my tea. It's very special. You're gonna laugh when I pull it out of here. I actually keep it wrapped in a plastic bag inside a tin because it's a very fragrant tea. It's a Lapsang Souchong, which is a smoked black tea leaf. Smoked in preparation, not smoked like, not like a cigarette. But then it's soaked in, allowed to ferment in bourbon barrels. So it is very fragrant. It smells like malt and vanilla and bourbon and Lapsang Souchong. It's a very pleasant smell if you like studies with leather chairs and old pipe smoke smell to it, pipe tobacco and bourbon and old books. Once again, I have my disposable tea bags that I compost. Because as much as I try, I don't seem to be able to wash the reusable ones very well. This is what these look like. They're made out of unbleached paper. They're a nice little sound to them. I also have my old-fashioned teaspoons. These look like something straight out of Grandma's kitchen. This is what the tea looks like. You can see it's got, it's just a regular black tea look to it. It smells really good. It's very sweet, kind of sweet smell. If you like vanilla, you would like this tea. It's very powerful, though. It's even more of a distinctive flavor than Lapsang Souchong, and some people hate Lapsang Souchong. I don't. I love it. Especially in the winter time, which it's not quite yet, but soon. I just did that to tap on the bottom of this tin, and I realized it's the first time I've looked at the bottom of the tin, and it actually tells me how to prepare tea. Which would be useful if I didn't already know how to do that. It's good to know it's there for future reference. Teacup today is my blue one, blue glass one. That was given to me by my high school sweetheart the day I got my senior pictures taken in high school. I've had it a very long time. I used to drink orange juice out of this cup before I drank a lot of tea, before I drank coffee even. I didn't drink coffee much until graduate school because I really liked, I drank orange juice out of the cup because I liked the contrast of the colors, the orange with the blue. I thought it looked really pretty. Alright, now because it's a black tea, it will steep a long time before I really want to drink it. You want to get a lot of flavors out of it. You gotta let it sit for a while. So while that's steeping, let's have a little conversation about chemistry, and in particular, the thing I wanted to talk to you about today. This is one of my fun things. This is one of my fun things that I talk about with particularly my littlest son. He's 7, and he does not like to sleep. So when he is lying in bed getting ready to sleep, he will ask me outrageous questions. So I started giving him lectures on some of the things we've talked about here, so or will talk about in the future. How the brain works is one of them. Yeah, that was one of my specialties. I don't know if you probably talked about that in other videos, but I used to do neuroscience research, so I have a pretty good understanding of the human brain, the brain in general, other brains as well, mostly mammalian. I've done other research as well, genetics research. We talk about genetics sometimes, how that works. And one of my favorite topics in college was chemistry. And one of the things that I really enjoyed about chemistry was once I understood how electrons filled up orbital shells in individual atoms of an element, it made understanding the properties of that element much easier. Made all of chemistry a lot easier once I learned that. So, and it follows a pattern mostly. So I was going to talk a little bit about that today. So I'm going to start with something that I enjoy from They Might Be Giants. They made an album called Here Comes Science, and there's a song in it called Meet the Elements, and the chorus of that song is like a box of paints that you mix to make every shade. They either combined form a chemical compound or stand alone as they are. That's what chemical elements are. I really liked the analogy of a box of paints. You could think of them as like Tinker Toys as well. They're all the basic things that you plug together in different configurations to make everything that we have around us. It's pretty fascinating. So if you look at an individual element, if you've taken, I think, high school chemistry, they cover it. There are 3 basic elements. Three basic components of an element. There are protons, there are neutrons, and there are electrons. So I'm going to draw a picture here. Protons have a positive electrical charge. This is a circle with a cross in it to indicate positive electrical charge. Neutrons hang out and they don't do anything. They're electrically neutral. They don't have a charge. And then electrons have a negative charge. Draw one here. Right there. Now, protons and neutrons generally just glue together in the center or the nucleus of an atom. Electrons, though, they like to move. And typically, it's not a particularly good circle, but typically they're depicted as having a circle, traveling in a circle or an orbit around the central nucleus made up of protons and neutrons. But electrons actually don't travel in a nice neat circle like this, or sphere. If you think about it in 3 dimensions, it's a sphere, right? They form patterns, and these patterns are called orbital shells. It depends on how much energy. In this case, we can think of energy as how many electrons are orbiting the nucleus. And generally, when we talk about elements, the number of protons in the nucleus is going to balance the number of electrons in the outer shells. Not always, though. I'll get to that. So actually I can do it on this picture. So if you have one electron spinning around, it's in the first level of orbital shell, which we call 1s. Now you'd think that the S stood for sphere, but it doesn't. I don't actually remember what it stands for. I think it's sharp or something like that. The initial 3, I think, were used. They used the first letter of a descriptor of what the I can't remember the name of it, spectral graph or whatever, looked like when they were observing it, and so there was a sharp peak, so they called it sharp. I never remembered it that way. I always thought of it as sphere because it is sphere shaped. The first orbital is actually a sphere, first level orbital shell. And so we write this as 1s1, a little superscripted 1 there to show that's 1 electron in the first orbital. You can have 2 electrons in s orbitals. So I'm going to write another one right here. Okay, and that would be written as. So here's the other one, right down here. That'd be 1s2. Now, you can't have the 2 electrons there without having another proton in here. So I'm going to draw another proton for now. When I talk about it more, I'm not going to add in more protons because it's kind of a pain. I'm talking about electrons today, not protons. Okay, so there's your 2 protons and 1 neutron holding them together. 1s2. Now, you can keep adding electrons, but they're going to go to the next level. And the next level is level 2. I know that's surprising. And it's also an s orbital. 1s2. And there's a 2s. So it's also a sphere. And it's the next level out, and it's going to be bigger than the first level. I'm going to draw that on here. Okay. And I'm going to put 2 electrons in that one. And I'm just going to make a big blob in the middle for the nucleus. So I don't have to keep track of that. Okay. So there it is here. 2 s orbitals. So this is 1s2, 2s2, is how we would describe the electron configuration of this particular atom. But there's another orbital in the second energy level. So it's also a 2. And this one is called P. And again, I don't remember what the P stood for. And it is not parabolic, but that's how I remembered it, because they look like parabolas. They look like dumbbells. There's not a good way for me to draw it on here. Well, I could. So now it looks kind of like a flower, right? This is the dumbbell shape I was telling you about. Let's see if I can do this. So there are actually 3 subshells that are this shape. There's one that goes along this direction, one that goes up and down, and then one you can imagine if one came out of the paper at you. So they go one in each direction, this way, and this way. And these are called the p orbitals. And you can fit, because there are 3 of these you can fit 6 electrons in this shell. So 2p6. So if this were completely filled shells, you would have 1s2, 2s2, 2p6. Then we get to the next energy level, level 3, which, you guessed it, I hope, the first level, the first shell, is an S shell, and it can take 2 electrons. It's bigger. And do a good job of making it bigger. It should actually surround this. It's even bigger than the 2 level. So it contains the 2p orbitals inside it. Now we get also a 3p level, and then there is a 3d level. And D is a really hard shape to describe. It's kind of like it's hard to draw it as a graph. It's because of the way it's convoluted. So I'm not going to try. But the interesting thing about 3D is that it's very close to the 4s level, the next level up. So sometimes when the D shells, which there are 5 of, there are 5 D shells, so you can put 10 electrons in there. Sometimes when you get toward the end of that, when they're packed in close, one of the electrons actually kicks up to the 4s level. And why that's interesting to me, and I don't know if this is accurate and I remember it correctly, but I do remember a little bit about it, is that when an electron jumps between levels, it emits a photon, which is a light particle. And the wavelength of that photon, so the color of light you see, correlates with the distance between the orbitals. Isn't that cool? Sorry, I think that's really awesome. So that's how you end up with lustrous things, luminous things. And that's how you know, that's how they produce color, which is kind of cool. Anyway, excitation is when the electrons jump. They'll jump up when they absorb energy. So, right, I drew all those things out. Why is this important? Put that over there. If we look at, there's that nucleus again. I guess I didn't need to draw that as a nucleus. If we look at our electrons and we look at the shells, I think my tea is done steeping. I'll leave you hanging there for a minute. Okay, so collapsing the shoe shell. Oh, right, it's the conductive bourbon. Oh man, I forgot how good that is. Alright, so we were talking about electrons filling orbital shells. So I said each shell, each subshell, can contain 2 electrons. Now, why is that important? Electrons have spin, direction. I'm not going to explain this exactly right because we're getting into quantum stuff and I could never hold the quantum information in my head. But you can think of it as they can point in one of 2 directions. I remember this from the diagram in the book. They can point up or they can point down. So if I have 1 electron and it goes into my 1s orbital, I'm just going to draw that as pointing up here. It could point up or down, it doesn't matter. It can go in either direction. But the next electron that goes in there has a choice. It can go up or down. But if you have 2 pointed in the same direction, because they're electrically negative, they will interact with each other. So you might know this from magnets. Electricity and magnetism go together. So if you put two with the same charge next to each other, they'll repel. So it will actually increase the energy that's available in the shell. So what you want instead of that happening is what they will want the most stable configuration, which is to have one going in the opposite direction. That is the most stable configuration for it to go in, so that is what will happen. You can add energy to the system to make them go in parallel, but that's not the typical way of that's not the natural way that they'll go together. So you'll have one up and one down in the 1s orbital, one up and one down, and that's true for all of the subshells. So in the 2s orbital you have one up and one down. That's just naturally how they'll fill. But in the 2p's, when you get to the p's, rather than, I'll make these a little darker in between because I want to have a separation. So remember they had the X, Y, and Z directions, right? So rather than occupying the same subshell, they'll actually fill each individual one first. So you'll end up with this. 3 pointed up, because you'll have one in each subshell. But what makes an atom really happy is to have all of its shells filled. So, have its electron shells all filled. So when you look at I'm going to do water, but I'm going to have to think for a minute. So water is oxygen and 2 hydrogens. And hydrogen is the first element. It has 1 electron. Okay. Oxygen is the 6th element. I have to look and make sure that's right. So in the periodic table of the elements, they're listed in order of number of electrons, basically. So I just need to make sure I have that right. Carbon is 6. I knew that. And if I thought about it, I would have figured that out, but I didn't. It's okay. So, oxygen has 8 electrons. Okay. So oxygen has 8 electrons. So it's going to go and fill its orbital shells as 1 up and down, 2 up and down, and then there's actually one more here. So this is 1, 2, 3, 4, 5, 6, 7, 8. Oh, I can't write it that way. So you'll see it has 2 openings in its subshells, and the hydrogen has just 1 electron. So hydrogen, there's the hydrogen here that I drew earlier. It's got 1 electron here. Each one of these has 1 electron. And the oxygen has its cloud of electrons around it, but it's got 2 spots that are open. So what happens is that the hydrogen donates its electron. It shares it with the oxygen. Right here. So it's going to put it in this outer p orbital. Now what this does is basically puts this subshell shares itself with a hydrogen, and this subshell shares itself with the other hydrogen. So it creates an electrostatic bond. Covalent bond? Covalent bond. Electrostatic, it's different. Covalent bond. Co meaning together, valent meaning valence shells are what they call the orbital, is another word for orbital shells. So covalent, they're sharing electrons together. So you end up with your chemical formula, H2O, or dihydrogen oxide. You may have heard those funny sites about how dihydrogen oxide causes cancer and stuff. This is the joke that they're making. If you follow the standard naming convention that's come up for chemicals, new chemicals, this would be dihydrogen oxide, 2 hydrogens and an oxygen. And that's the chemical formula for water. And I drew it here molecularly because it's actually bent like this. It's a bent molecule. Why it's significant and really critical for the evolution of life as we know it is a story for another time, but it has to do with the fact that oxygen and hydrogen are configured in a bent shape like this. Also explains 6-point symmetry. I'll get to that some other time if you're interested and want to know about it. Anyway, that's how electrons fill orbital shells in atoms of elements, and it gives you one example of why that's important to understand how chemical compounds fit together and how what the expected reaction will be if you put them together. I found it fascinating when I was learning it. I think it's really neat. This is a very simple set of rules to follow, and it explains so many things. I hope you enjoyed this, and if you didn't, I hope it at least put you to sleep. It works with my son anyway. I'm going to finish my tea. I hope you have a good day. Thanks. Bye. See you later.